Hello everyone. In this video we're going to continue our Python series and continue our look at functions by coding up 3 different functions that all produce the Fibonacci sequence, and then we're going to learn a little bit more about functions along the way. So if you've never seen the Fibonacci sequence before, which is maybe surprising if you've studied computer science at all or tried to learn a coding language, you usually see this pop up, so we're kind of following suit, but it is a great simple example to really understand different ways of working with functions or iterating through things or generating some data. There's many ways to go about it. So the thing that makes the Fibonacci sequence special is that you have these two, I'm going to say initial values of 1 and 1, but then all the other values say, well, what if I take 2 and I add, or to find this, I guess, new value, let me take the 2 previous and add them together. And then to find 3, I'll add 1 and 2 together. And to find 5, I'll add 2 and 3 together. To find the next, I'll add 3 and 5 together. So you always are adding your 2 last known results, so to speak, to get any new value out of the sequence. So what I would encourage you to do is I would encourage you to maybe pause and try to see if you could write your own code that would generate this sequence. And I'll give you a hint and say that you should, at least somewhere in your code, start by saying, I know that the first value I'm interested in is 1, and the second value I'm interested in is 1, and then see if you can generate the next value and the next value and the next value using some Python functions. Now, that is kind of a hard task if you've really just been following along this series so far. We haven't really talked about algorithms and that kind of thing, but hey, that's what we're here to do in this video. So again, hopefully you gave it a really good attempt and try, because seeing the answer after you try is just going to make it that much more impactful, and you'll see, oh, that's what I could have done, or that's what I didn't see I could do, or I wouldn't have thought to do that, but hey, that works. So let's code up 3 different examples of getting the Fibonacci sequence. The first one I'm going to do is I'm going to call it basic fib, and what I'm going to need to do is I'm going to need to provide an n. In other words, I want to know what value do I want to know. Do I want to know the first value, the second value, third, fourth, fifth, or sixth? That's what n is going to represent. Now what I'm then going to do is I'm going to say, well, if n is equal to 1, in other words, if I want to know the first value of the Fibonacci sequence, or I want to know the second value of the Fibonacci sequence, well, then I know what that is. It's going to be 1. So I'm calling this the first value, and I'm calling this the second value. Some people might say the Fibonacci sequence starts at 0, and that might be true, but for this sake, we can just say it starts at 1 and 1. Right? So if I want the first value in the sequence or the second value in the sequence, well, both of those are 1, so I can just return 1. Cool. Now, else, and I don't need to write else like we talked about last time, because either this is going to be true and we'll return a value and break out of the function, or otherwise, so I don't need to write else, I can just continue down the line. What I'm going to need to do is I'm going to need to say the smaller of the 2 values, or maybe I'll say 2 steps back is equal to 1, and I'll say 1 step back is equal to 1. So in other words, if I wanted to know the third value, I need to look 2 steps back and 1 step back and add those 2 prior values. So what I could then do is I could say, and well, we're not going to get the right answer here, but I could say return 1 step back plus 2 steps back. Now, this isn't going to be our full answer, but what you can see here is that, okay, now I at least have a way to add the prior 2 values, right? But right now, this is not going to give us the right answer, because this is only going to get me up to the third value right here, 2, and I'm not really going any farther. I'm not using this n outside here. So what are we going to do about that? So if I know that 2 steps back at this first place I'm at 1, and at this value I'm at 1, well, then the question is, how do I get all the way up to 5? And that's where we're going to need a for loop. So we're going to say for we're going to put a underscore in here in range n minus 2. Now that underscore is not a special Python like keyword or like for loop variable. It literally just means, hey, I just need to iterate a certain amount of times, and I'm not actually going to use this value. And that's kind of a Python coder's way of saying, I know I just need to iterate through something a set definite amount of times, and I just don't actually need that value in my code, so I'm just going to put an underscore there. I need to iterate somehow in a for loop, but I don't need the value of the for loop, so to speak. So there we go. So for a certain amount of steps in range n minus 2. Now, why is it n minus 2? Well, because we've already figured out the first 1 and 2 values of the sequence, so we don't need to find the third value, do 3 iterations. We just need to do 1 iteration, 1 set of addition to get the value 2. Now, here's the big question of how am I going to increase the value? And this is going to be kind of a big trick here, or it takes some time to wrap your head around this, but what we're going to do is I'm going to say I'm going to store a temporary variable, and I'm going to call that the 1 step back, and then I'm going to say I want 1 step back to now be equal to 2 steps back. Sorry, I don't want it to be equal to, I want it to be increased by the value of 2 steps back, and I also want the 2 steps back to now be equal to my temp. All right. And believe it or not, now I don't need to return the addition of the 2. I just need to return the 1 step back. And we've actually done it, and we're going to have to explain this code in a little bit here. So first, let's just see that it works. If I want basic fib 5, if I want the 5th Fibonacci number, so let's be careful, 1, 2, 3, 4, 5. Well, that actually is 5. There we go, it spits out 5. If I want the 7th Fibonacci number, then I get 13. So that looks like we're working nicely, and now I could even figure out what the 246th Fibonacci number is, and it gets pretty big pretty quick, but at least I was able to calculate it. So there we go. We've done what we would call the simple iterative Fibonacci sequence. Now let's take a minute to break down what's going on in this line of code here and why we're structuring it this way. So what's going on here is, well, if I wanted to, and let me write this out. So let's say I had 1 and I had 1, and I did not know what this next value was. All right, what our code is doing is it's saying, I'm essentially not going to remember the entire sequence. I'm just going to hold on to those last 2 values in the one I'm currently interested in. So in other words, because I want the third value, right, we're going to say, okay, let me remember that 1 was the value that I last knew that I was trying to get to my next value. So I last knew this 1, and I'm going to call that my temp. So 1 step back from what I want to know. And then what I'm going to do is I'm going to say I now want this value here to be increased by the value of 2 steps back. So this is now going to be 1 plus 1, 1 plus the prior amount, which is 2. And I then want the variable 2 steps back to be equal to temp, which is actually still 1. Now, because of the ones, that didn't quite look right, but let's go through one more iteration and now go through this for loop. So let's say I wanted to find the 4th Fibonacci number, right? What we just did was we just calculated the 3rd Fibonacci number. We now know it's 2. So how would I calculate the 4th Fibonacci number? Well, I would have to iterate through this step one more time. So temp is equal to 1 step back. So 1 step back is now 2. And now 1 step back is going to have the last value added to it, which becomes 3. And then 2 steps back is now equal to the temporary variable. So there's a little bit of shuffling going on there, but now I can get 3 out of the Fibonacci sequence because I can now return what's 1 step back. So in other words, it's like these 3 values here are kind of sliding along and calculating the next and the next and the next by saying, okay, I need to hold on to this 3 for a minute. I need to add 2 to it to know that the next number is 5. And then I need this value that was 2 to be the 3 that I was holding on to from before. So maybe go through it a few more times and write down this example. In fact, I think we will go through one more iteration just to really drive it home. So if I have gotten up to 3, right, and I want to know that I get 5, then again, I hold my last known value in a temporary variable. I then add the 2 steps back to that position that I was just looking at, which would be 5. And then I now make the temp, I make 2 steps back equal to the temp, and there we go. So it's a pretty simple process, but it's kind of the big clever trick here is that you need to actually have a third variable in there, a temporary variable, to hold on to the value while you're switching them out for one another. That's the big key there that you might not have known to do. Great. So we've done an iterative approach and it works. So I think that's good enough for now. I know it takes some time to get used to this. And again, the other idea that we're learning here is, or seeing, hearing, learning, is that in your for loops, you don't always have to use the value that you name as like your incrementer, so to speak. It just needs to be there. And if you don't use it, we usually just put an underscore to say, I'm not actually using it. I just know that I need to do something a certain amount of times, but I don't have any data to pass into it or use. All right, so there we go. Basic Fibonacci, and we're done. Let's now learn about what I'm going to call memoization. All right, so what we're now going to do is we're going to go through the basic Fibonacci sequence, but we're going to get away from this kind of nasty logic. So this solution that I'm about to show you is actually my favorite, and it's a pretty simple one. But we need to learn about something called memoization, or in other words, we're going to be storing our results. We're not just going to be holding on to two values at a time and starting from the beginning every time. We're going to be holding on to all the Fibonacci values as we go along. Now, that's a big trade-off because maybe you don't want to hold on to all the Fibonacci numbers inside of your computer's memory. So there is an advantage to this one. It's that you're only actually holding on to two values at a time. I guess the temp makes a third. But besides that, you don't hold on to any other values. The drawback is because you are only holding on to two values, you always have to start at the beginning of 1 and 1 and work your way all the way up. So let's see what we can do with creating a memo. So I'm creating a memo list, and now I'm going to call this my memory fib. And we still need to take an n to figure out what value we want. All right, now let's say I want the second Fibonacci number or the third Fibonacci number. Then what I'm going to do is I'm going to say, well, right now I only have two Fibonacci numbers. So how can I do that? Or how can I figure that out? I can say, while the length of my memory list is less than the value that I'm trying to get. So, right, if I pass in, I want the first Fibonacci number, well, the length of my memo is 2, so I actually won't do anything in the while loop. And if I want the value 2, right, then is 2 less than 2? Also, no, it's not. So if I wanted the second Fibonacci number, my memo's already long enough to get out of the while loop directly. So if that's the case, if I've already gotten out of the while loop, then I can simply return that I want memo at the index. Now be careful here, n-1, because if I want the first value, I'm getting from the list at the 0 index. And if I want the second value, I'm actually getting things from the first index. So I need to return the value at the memo at the -1 from where I'm interested in, because if I want the first Fibonacci number, I need the 0 index. If I want the second Fibonacci number, I need the first index -1. All right, the last thing to do is figure out, well, what if I don't have the value? What if I want the fourth value and I only have two values? Well, then what I can do in this while loop is I can say that I want to append, and this is where this gets a lot simpler. I want to append my last known value plus the second to last known value added together. So that's pretty nifty right there, and believe it or not, we're already done with our function. That does everything we need to. Let's try it out. Let's try memory fib, and let's say we wanted the fourth Fibonacci number, which is 3, and we saw that before. So great, we're getting the same answer. Let's say I wanted the 40th Fibonacci number, and now I know what it is. Again, they get pretty large pretty quick. But here's the big trick. If I now look at my memo is actually holding on to all the values I found before. So that's actually pretty interesting, because if I want the 400th value, all right, I've now calculated up to the 400th value. And what I want you to think about now is, now that this memo is actually 400 units long, what now happens if I ask for memory fib 30? Right, so really stop, pause, think about that. What if I ask for memory fib 30, knowing that I can see my memo now and it's at least 400 units long? Well, what's going to happen now is that this while loop is never going to occur because it's saying while the length of my memo is less than n. Well, 30 is n, and the length of my memo right now is, I think, 400 values stored in there. So 30 is less than, 30 is not greater than the length of my memo. So I actually don't need to do any appending, and I'm actually just going to return the value right away. So that can be pretty useful because let's say for some reason you needed to know the 300th Fibonacci number and then you needed to go back and figure out the 50th. Well, actually, if you think about it, you're not really going to spend any time calculating in this function because you've already stored that value in your memo ahead of time from the bigger calculation you had to do. So cool. This one is, again, iterative. The benefit here is that you're only holding on to 3 small variables at a time. Now, this one is still iterative in a sense, but in fact, I would actually argue it's kind of more recursive in a sense. But and we'll talk about that more directly in a second with this next one where we exclusively do recursive. But the last thing to say here is what we now have is we have less work in code to kind of write. But what's costing us now is our memory, that we're now hard coding and storing the Fibonacci numbers as long as this Python kernel is up and running. So you either have to store the values that you last knew and you can write a lot less code, or you need to not store the values and you might have to write a little bit more code and always start from the beginning. All right, so the last one is the recursive fib, and recursive is really tricky to figure out. So here we go. We're going to say recursive fib. And once again, we're going to provide n. So hopefully you see that there's a little bit of a similar structure between all 3 of these. Now this is where things get really interesting. Just like before, we're going to say if n is 1 or 2. Now another way of saying that is just if n is less than 3, return 1. All right, so again, if n is less than 3, if I wanted to know the first Fibonacci number or the second Fibonacci number, then I just want to return 1. All right, first Fibonacci, second Fibonacci, they're both 1. So if the input I get is less than 3, just return 1. Now this is where things get really, really wacky. We can then say else, or actually, again, we don't need the else here. We could then just say return, and this is where things get really wild. Recursive fib n minus 1. Plus recursive fib n minus 2. Now, this code here is, again, pretty small and pretty condensed, and you should look at it and actually say to yourself, hey, that actually looks more like what we did up here. There was a minus 1 and a minus 2, and we were adding them together right there inside of like some kind of memory. And this looks pretty similar, but the difference here is that this is accessing items of a list, and this is actually running the entire function. Now, this is kind of hard to explain in video, but we'll do just in a code editor, but we'll do our best to write down exactly what's going on here. So let me change this to Markdown and try to type out what's going on here. So what's going on with this function is, let's say I wanted to know the 5th Fibonacci number. Well, 5 is not less than 3, so we're not going to return 1. So instead, what I'm going to do is I'm going to return Fibonacci 4 plus Fibonacci 3. But then you're going to say, well, Fibonacci 4, I don't know. All right, so in other words, I need Fibonacci 4. Now that's a function there. So Fibonacci 4 says, do I know Fibonacci 4? Well, 4 is not less than 3, so no, I don't. Now how do I figure out Fibonacci 4? Well, I'm going to need to figure out Fibonacci 3 plus Fibonacci 2. All right, so in other words, maybe I'll even write it down like this. Fibonacci 5 is Fibonacci 4 plus Fibonacci 3. Fibonacci 4 is equal to Fibonacci 3, plus Fibonacci 2. All right. Now, not only that, like in other words, we have to do that for figuring out Fibonacci 4. And even though we're going to figure out Fibonacci 3, notice we're not storing that anywhere. There is no memo here. So we're also going to have to simultaneously figure out Fibonacci 3 for this part right here, even though it's already being asked again over here. So how do I figure out Fibonacci 3 over here? Well, again, 3 is not less than 3, so I'm going to have to say Fibonacci 3 is equal to Fibonacci 2. I don't know what was up with my spacing when I did this, but oh well. Plus Fibonacci 1. Last but not least, there's one more thing because we're not quite done yet. We need to figure out the Fibonacci 3 over here. So if you're keeping track, I'm kind of trying to space it nicely. I wanted Fib 5, which means I needed to know Fib 4 and Fib 3. I don't know Fib 4 or Fib 3, so in order to find Fib 4, I need 3 and 2. In order to find this 3, I need 2 and 1. Last but not least, in order to find this 3, all right, in order to find that 3, I need to find Fib 2 and Fib 1. Okay, now where does the power of this function go or occur? Because it seems like we're repeating a lot. Well, finally, if we look at this bottom level, and we sometimes refer to this as a base case in recursion, Fib 1 is known. It's going to be 1. And Fib 2 is also known. It's going to be 1. All right, that's what we get from what we call the base case, that early return. So I now know that Fib 3 is equal to 2. Well, great. Now what I just figured out was this Fib 3 right here. I figured out that that Fib 3 was equal to 2. From there, I needed to figure out this Fib 3, and I know that this is equal to 1. I know that this is equal to 1. So I now know that this Fib 3 is equal to 2, which corresponded to this one over here that's now equal to 2. I now needed to know Fib 2, which was equal to 1. 2 plus 1 is 3. And I now know Fib 4 is equal to 3, which means I now know Fib 5 must be equal to 5. Now, hopefully you followed all that logic, and all of that logic has to occur. And what I hope you realize is that this is why recursion can be kind of messy, is that you end up like, just for finding Fib 5, we needed to, let me go back and actually undo this for a second. To find Fib 5, we needed to run through 1, 2, 3, 4, 5, 6, 7, 8 different items to figure out the fifth Fibonacci number. So 8 calculations to get the fifth value. That seems like a lot of calculations, whereas these are doing a lot less per calculation. You know, if I want to know the 10th value here, I'm actually just doing 8 calculations because I already knew the answer to the first 2. So hopefully you kind of see that recursion can get a little bit messy, but there is kind of a beautiful simplicity to this function. You actually don't need a for loop or a while loop at all. And that's pretty darn clean, but it takes a while to understand that you need a base case. You need at some point to just return 1 and not simply end up in a loop of saying, I need to know the last value. We need to know the last value. We need to know the last value. How did I get the last value? Now, maybe the final way to explain recursion is that recursion essentially says, I don't know the 8th value, but I know to find the 8th, I need the 7th and the 6th. And then you're saying, well, I might not know the 7th or 6th, but to find the 7th, I just need the 6th and the 5th. And the last part about that, you follow it all the way down until you say, well, I know the first value is 1 and I know the second value is 2, and you're done. I think the issue with recursion to me is that recursion ends up doing the same calculation over again. I needed Fib 3 to answer this right here, but I also needed this Fib 3 to answer this right here. And unless I'm storing that in some sort of memo along the way, I'm kind of running into another situation where I'm doing repeated work that I might not need to, especially with recursion. So what that might mean is that you could actually do a memoed version of recursion as well. But I think we'll just hold off on that for now and move on. The last thing I want to do with this is I want to show you the 3 different runtimes of these, and we're going to learn one important lesson, and that's that you can put functions inside of functions. So here we go. I'm going to for the first time, I'm going to import a module. I'm going to say from time, import time, and we'll talk about imports a lot on a new video after this. But for now, just know that your Python comes with this module time, and you can use the time function inside of it. So what I want to do is I want to time these three and see how they do. So let's do time my func. And I want the func, and I want the val. So in other words, what I'm going to do is I'm going to say I don't know which function I'm going to use, maybe the recursive, maybe the memory, maybe the basic fib, and I want to know the 5th value or 10th value. I'm not sure yet. So I know that I want to time my func. So from there, what I'm going to do is I'm going to write start is equal to time. Now what this does is it essentially grabs hold of the exact time that it is right now, and it's going to store that in a variable start. What I'm then going to do is I'm going to print out the function at the value, and then I'm going to print the current time minus the start time, and that will tell me how many seconds this took to run. Now, what's going on that's really, really cool in this function is that notice what I'm doing is I'm creating a function that takes in a function and then runs it inside of the function. We call this higher ordered functions, but I think this is a great way to just expose yourself to them by just saying, what if you just wanted to time the runtime of your code? Well, then what would you do? You need to know when you started your code by calling that function, that timer function, and then that would essentially say, well, let me grab hold of the time it was right before I ran the function. Now let me run that function, and now let me figure out how many seconds it took, because now the function stopped running, so I can call a new time and compare it to my start time. All right, so every time you write time, sorry, that's a lot. Every time you write that time parentheses, you're creating another record of the exact moment in time. So we're storing that start time, and then we're just getting the current time and comparing them really quick afterwards. The very last thing to explain here is to do a higher ordered function. Notice I just need to write the word func, and I don't need to actually put the parentheses in there. Notice that the parentheses are applied to your function inside the indentation level. So it's saying I'll just hold on to the name of the function, and then I'll call it and put the value inside it once I'm inside of that higher ordered function. Okay, great. With this armed, we're now ready to calculate some run times. And I'm also going to restart my kernel here so that my memory fib is starting from 0 or its initialized value and isn't holding on to any stored values. Okay, great. So let's just now define all my 3 different ways, because I need to define them in order to be able to run them. Great. And let's run all 3 of them. Now to do this, I've snipped some code from earlier just to speed up time here. And let's see how long it takes each one of these to figure out the first, the 30th Fibonacci number. All right, so they all got the right answer. And what I want you to notice is that the recursive fib went pretty quick. Now also the basic fib went even faster. If you don't know what this notation means, it means move the decimal back 5 places. So there are actually 4 leading zeros. And this one also move it 5 places back. There's 4 leading zeros. So right now, actually, the recursive fib is the slowest of the bunch because it didn't even need that move the decimal place over because the number's smaller than you think notation. So, cool. Fibonacci sequence was actually kind of slow, and that shouldn't be too surprising. The simplicity of recursion in this case is that it takes so little to write, and we don't actually need loops written into the code. It's kind of a more so if you don't need that many values, it can look pretty nice. Now what I want to do is I want to run this one more time and show you the power of the memory fib, because right now the basic fib was a little bit faster, the memory fib was slower. In fact, 1.8 compared to 2.0, they have the same E. So this one was just a little bit faster, and these are microseconds, so it's not like you would ever notice actually running these, but they were pretty close. But let's run it one more time and see what happens now. All right, now look what happens. The memory fib wins out. Now, why does the memory fib win out over the basic fib? Because they both beat recursion. Well, because now, if you think about it, the memory fib has already stored the result of 30, so it actually isn't iterating through this while loop at all. It's already gotten up to length 30, so it's just able to return the value right away from the list and not iterate through from the beginning. Whereas the iterative fib had to start all the way back at the first and second value and work its way back up to the 30th every single time. Now, let's really go crazy here and find the 300th Fibonacci number. And I think we might even break recursion because recursion can't go that far in depth, but it will try. Now, what you're seeing right now is you're seeing the recursive function not actually able to finish quickly, because remember what we said, the big flaw with recursion is we are not currently storing prior answers. So we're going to have to refigure out fib 298 multiple times. We're going to have to figure out fib 297 multiple times as we're descending down the tree, so to speak, all the way down to fib 2 and 2 and 1. So in fact, I think this is even long enough just to say, well, let's just stop and throw recursive out because it took over 40 seconds. So let's throw that one out and just look at the other two. All right, so great. You can see that the iterative and the memory were really darn fast. And again, what we're also going to see is we're going to see if we run this again, now that the memory fib has stored up to the first 300, it's definitely going to go super fast. So it still has that e to the negative fifth, meaning there's 4 extra zeros. Now my iterative only has 3 leading zeros. Let's go to the 3000th. All right, and see how they compare now. So right now they both have about the same runtime, right? Because they both had to get all the way up to the value. But if I run it again, now my memory fib has already stored the answer. Now, we've been increasing this every time. The other benefit of the memory fib is that if I go down a level and I go back to 2000, memory fib already has the 2000 answer because it's gone up to the 3000th answer. So hopefully you see that there is definitely some benefit to storing your prior results. Just know that now somewhere our RAM is being filled up with all of these numbers, which won't fill it up too much, but if we were maybe to push this up to 20,000, things would start taking a while, and our memory would become pretty darn full. So also, if you notice here, it's still running pretty quick, but now even the memory fib is taking some time to get all the way to the 20,000th value. But it's definitely beating out the basic fib because the basic fib still has to start out from 1 and 1 every single time. So I really hope that kind of made sense, and I hope you got a lot out of this video, that there's many ways to even just handle a simple Fibonacci sequence in many different ways. And we were also able to learn about higher ordered functions so that we could time our code. And we'll see more in the next videos.